want you to call me. I said if you need me, all you gotta do is call me. Don't wait too long if things go wrong.
Okay, section 5.7 is review exercises, and this is probably a completely unnecessary section. I'm going to do another one of these curve sketches. I think I've done that the last 3 videos or something. My main reason for doing this is to show you the format of 2 of the humongous questions that are going to be on your chapter test. So you have 2 questions like this one. So I want to show you exactly what it looks like, what I expect you to do for your answers. But you should already know everything we're doing here. So I'll do this quickly. Excuse all the noise in the background. There's a photo shoot going on here. There's someone vacuuming. Ambulances going by. It's a gong show here. Okay, so here we go. Here's what we're graphing. F of x equals x over x minus 1. So I want to know the domain. For domain, you look for square roots. There is none. You look for denominator. There is one. What needs to be true is that x minus 1 cannot equal 0, which means x cannot equal 1. So that's what you'd write in here. Don't show your work in here. Just put your answer. X cannot equal 1. This will make it much easier for me to mark. Y-intercept. Well, to get the y-intercept, you put 0 into the x's. So you would have y equals 0 over 0 take away 1, which is just 0 over negative 1. It's 0. So your y-intercept is 0. I don't mind if you put 0, or you could put 0, 0. X-intercept, we put 0 where it says f of x, or y, we put 0. So you get 0 equals x over x minus 1. Multiply both sides by x minus 1, so you're left with 0 equals x. Oh, so again, you can either put 0, or you can put 0, 0. Symmetry, we put negative x in here. We want to know what f of negative x equals. So you'd have negative x on top, and on bottom you'd have negative x minus 1. Is that exactly the same as what we started with? No. Is that the negation of what we started with? Almost, but not quite, because the negative 1 stayed the same. So it's not odd, it's not even. You'd put none, or neither, or I suppose not applicable, whatever. Equation of slant asymptote. Well, you get a slant asymptote when the degree of the numerator is 1 more than the denominator. Degree here is 1, degree here is 1. They're the same. What's that mean for slant asymptote? None. Equation of vertical asymptote. Vertical asymptote, wherever the denominator equals 0, we already figured that out. It's when x equals 1. So that's the equation of our vertical asymptote. X equals 1. One-sided limits near the vertical asymptote. So now that we've found our vertical asymptote, we have to find the limit of the function as x approaches 1 from the left, and the limit of the function as x approaches 1 from the right. So on the top, in both cases, if you put 1 in there, because it's okay to do so, you get 1 on top. So you're going to have 1 over, I could do it here too, I suppose. And then the bottom, a number a little bit less than 1, so like 0.999. 0.999 minus 1 is a very small negative number. So you're going to have a small negative here, which means when you divide, you're going to get negative infinity. Now, if you took a number a little bit bigger than 1, like 1.0001, and subtract 1, you'd be left with a very small positive. So small positive, which means you're going to have positive infinity here. I think it might be a good idea to also show what happens near that asymptote. So if this asymptote right here is at 1, which is where we already said the asymptote would be, x equals 1, we have found that when it's to the left of that, it goes down towards negative infinity, and when it's to the right of that asymptote, it goes up towards positive infinity. So we know that's going to be part of our graph. Equation of horizontal asymptote. Well, remember the fast way to figure out the horizontal asymptote? If the degrees are the same, like they are here, you just take the leading coefficient, 1, and the leading coefficient, 1, and divide them. 1 over 1 equals 1, which means the equation of our horizontal asymptote is y equals 1. Okay, we're ready to take the first derivative. I think I'll write it over on the side here. Again, I don't want to squish it in here. It's going to be too messy. So why don't I rewrite this right here, and I want to know what f prime of x equals, first derivative. So quotient rule, take the derivative of the top, which is 1, and multiply by the bottom. So you get x minus 1. Then you're going to subtract the top, which is x, times the derivative of the bottom. The derivative of the bottom is just 1, so you don't even need to put it, over x minus 1 all squared, the denominator squared, equals, well, x, take away x, those are gone. So all you're left with is negative 1 over x minus 1 squared. That's it. That's the first derivative. So that's what we're going to write in here. f prime of x equals -1 over x minus 1 all squared. We have to find the intervals of increase and decrease. How are we going to do that? We're going to get the critical numbers. Now, you don't need to write for me critical numbers, but you will need to figure them out. So, in order to get the critical numbers, you need to know, when does this derivative not exist? Well, that would be when the denominator equals 0. Take the square root of both sides, you get x minus 1 equals 0. Move the 1 over, you get x equals 1. That's one critical number. To get the other critical number, you want to know, when does this derivative equal 0? Well, that would be when the numerator equals 0. Well, that doesn't make sense. That's impossible. So you only have one number to put on your wiggle graph. Got the 1, which I'll put it right here. And we're going to test these two intervals right here. So notice you don't even need to check any numbers, because, can you hear the shower now going? Everything's so loud. We have a negative number on top, and no matter what we put in the bottom, when we square it, we're going to end up with a positive. Negative divided by positive is negative. It doesn't matter where we do this. You're always going to have negative and negative. Check out specific numbers if you want, but it's unnecessary. So that means it's going to decrease and it's going to decrease. So intervals of increase, nowhere. Intervals of decrease, be careful here. It's from negative infinity up to 1, as well as from 1 to infinity. You can't say from negative infinity to infinity because it's not decreasing at 1. Second page already, we are moving. Local maximum and minimum. Well, you could use a second derivative test, but let's just go back to here. We can just use this information right here. Decrease, decrease. Well, there's no maximum or minimum. It has to go decrease, increase for a minimum, and increase, decrease for a maximum. It's neither one of those, so none and none. Second derivative. Let me rewrite the first derivative here. Okay, here you go. This is the first derivative. Now, you could use the quotient rule, but you know what I would probably do here? I'd probably move the denominator up to the top. I'd have -1, or just negative, x minus 1 to the -2. Right? Take a second, look that over, and make sure you understand. You don't have to do this, but I think this will be easier. You don't have to use the quotient rule now. What rule do you have to use? The chain rule. So that's what I'm going to do. I'm going to use the chain rule to get the second derivative. How do I do that? Well, my outer function is this something to the -2. So the -2 comes down and multiplies by this -1. So that just equals 2. Keep the inside the same, x minus 1. This drops 1 to -3. And I take the derivative, I have to multiply by the derivative of the inside. But the derivative of the inside here is just 1. You don't even really need to put it. So if I simplify this, I'm left with 2 on the top. This is a flipping negative, so x minus 1 goes down to the bottom. It's no longer -3, it's +3. This is your second derivative. So f double prime of x equals 2 over x minus 1 all cubed. Intervals were concave up and concave down. Well, now we have to find our pips. So again, you don't need to write pips here if you don't want to, but you do have to find them. How are you going to get those? Got to find, when does this second derivative not exist? That will be when the denominator equals 0. So x minus 1 all cubed equals 0. Take the cube root of both sides, x minus 1 equals 0, which means x equals 1. That's one pip. The other place you'd find a pip is when the whole thing equals 0. That would be when the numerator equals 0. That doesn't happen ever. So this is it. You only have one pip. So we're going to put that on our wiggle graph. And we do have to actually check some numbers here. Let's try, where we're going to try them, by the way, right in here. So if we put 0 in there, we'd get 0 take away 1 is -1. -1 cubed is still negative. Positive divided by negative is negative. So this is concave down. If we put 10 in there, well, no, let's put 2 in there. 2. 2 minus 1 is 1. 1 cubed is 1. 2 divided by 1 is positive. This is concave up. So it's concave up from 1 to infinity. It's concave down from -infinity to 1. Then we're looking for point of inflection. This looks promising because it goes from negative to positive, and whenever it changes, it's could be a point of inflection, but it's not a point of inflection. How come? Because if you look back at our domain, we said that 1 was not part of the domain. So there's no point there, which means this is none. We are ready to graph this. I'm going to set it up here. You'll remember we had a vertical asymptote at x equals 1, so I'll put that in. And then we have a horizontal asymptote at y equals 1, so I'll put that in. And I think there's only one point we actually know in this graph. That one point is 0, 0, so I can put that. And we also know the behavior near the vertical asymptote. Remember this, these black curves here, so we can put those in. On the right hand side, it goes up towards positive infinity. On the left-hand side of this asymptote, this vertical asymptote, it goes down towards negative infinity. Remember that it's always decreasing. We saw that at the bottom of the first page. It's always decreasing, never increases. And so we're almost done. Let's see. When it is less than 1, it is going to be concave down. So we need to have it go through this point, end up here, and it's going to be concave down. It's going to get closer and closer to this asymptote. I think we can do this. This is all concave down, isn't it? And it's all decreasing, so that works. And sorry about that little move there, but you get the idea. And always decreasing, we said, up here, and it's concave up bigger than 1. So this will work nicely too. This will be concave up if we bring this down and get closer and closer to this asymptote, as you would expect it to do. And there you go. We said there was no symmetry. Does this have any symmetry? No, it doesn't. So I think this is quite encouraging. I think this is probably the answer. Good for us. And we did that pretty fast. You'll do 2 questions like that on your chapter test. Now, you won't be able to do this in your test, but wouldn't it be nice to be able to check to see how we did? Let's take a look. There it is. That's the answer right there. Look at ours. Look at there. Pretty good job. Way to go, class. You're ready for the test. Good luck to you.